that in a game, balls are thrown to hit a target. The random variable x is the number of times the target is hit in, important, 5 attempts. The probability distribution for x is shown in the following table. So, let's understand this a little bit more. Up top you have x, right? And so x, they told us, is the number of times the target is hit. So, number of hits. While down here, when they put the big P, parentheses, big X equals little x and all that stuff, all it's really telling you is the probability of that. And when I say that, I mean this. If the number of hits are 0, the probability of landing it 0 times is 15%. If the number of hits is 1, the probability of that is 20% with the 0.2. So notice how this is hitting the target 5 times. That is why the different scenarios is hitting it 0 times, once, twice, thrice, 4 times, or 5 times. Okay, that is why you have 0, 1, 2, 3, 4, 5 up top, and the probabilities of that are on the bottom. Just to further finish explaining what's going on here, the probability that you landed 5 times, so 5 out of 5 basically, is 25%. The probability that you land 4 out of 5 is 2k. The probability that you land 3 out of 5 is 0.16%. Okay? So that is what's happening. And for part A, all you need to do is find the value of k. So how the heck do you find the value of k from here? There's only one key piece of information you need to have in mind for this part. Okay? And that's the following. In probability, all your scenarios must add up to 1. And this, once you understand this thoroughly, you're going to be able to solve any probability problem. Well, almost any, okay? What do I mean by all my scenarios must add up to 1? When I say all your scenarios, by your scenarios, really, I mean all your probabilities. Probabilities must add up to 1. All right? This is the thing. You have 6 scenarios here for landing it. In this case, right? You're trying to hit a target 5 times. You have 6 scenarios. You either land 0 times, 1 time, 2 times, 3 times, 4 times, 5 times. There is nothing more, nothing less. You can't land it -1 times. You can't land it 6 times. It's only 0, 1, 2, 3, 4, or 5. And respectively, the probabilities have to add up to 1. Because there isn't a 6 here, and because there isn't a -1 or anything crazy like that, then you need to be able to cover all scenarios, so you have to cover all probabilities. In other words, all I'm really telling you is that over here, this has to equal 1. So for part A, it's a quite simple sort of line of math. All you need to do is add all the probabilities. So 0.15 plus 0.2 plus k, so that's these 3 right there, plus 0.16 plus 2k plus 0.25, which is these other 3. So all of these probabilities added together, as I say here, in probability, all your probabilities must add up to 1, all your scenarios must add up to 1, have to equal 1. Now some of you might be thinking, why the heck does it equal to 1? Well, that's the thing. Here you have a whole number, here you have a decimal, but this could also be percents. So notice, 0.15 as a percent is 15%. 0.2 as a percent is 20%. And so if suddenly you look at these as percents and not decimals, what you're actually doing is adding 15% plus 20% plus some k percent plus 16% plus some 2k percent plus 25% has to equal 100%. And that's the main idea I was trying to tell you earlier. This 1 is the same as saying 100%. Okay, so keep that in mind. It equals to 1 because it equals 100%. So all your probabilities added together, all your scenarios added together have to equal 100%. You have to be consistent in that sense. So whether you think about it in terms of percents or you think about it in terms of decimals, you have to acknowledge it has to equal to 1 or it has to equal to 100%. That it? So enough blah blah. For part A, well, you can pretty much just use your calculator here. And so on my calculator, I will be adding up all of these guys. See? So all of those guys ends up giving me we have 0.15 plus 0.2 plus 0.16, and on the other side we have 0.25. So those are the random decimals I have lying around, and I can also add up this k with this 2k, right, which is just going to be 3k. So for part A, what I end up with, all right, at the end of the day is 3k plus what I got from my calculator, 0.76, has to equal 1, the 100%. And so to get 3k from here, you can do minus 0.76 onto both sides. So 3k has to equal 0.24 divided by 3 divided by 3. K has to equal, I think it's 8. It's 8, yes. So k has to equal 8, all right? So the main idea here that you have to embark upon is that in probability, your probability has to add up to 1, has to equal 1, because you acknowledge all scenarios. So if you acknowledge all scenarios, it has to be one of them, right? So if it has to be one of them, it has to equal 1. All right, there's a couple ways to explain that. That's what I chose to do for today. That is for part A. Then they tell us that the player has a chance to win money based on how many times they hit the target. Okay. The gain for the player in money is shown on the following table, where a negative gain means that the player loses money. So if a player, for example, lands 0 hits, they lose $4. If they land 2 hits, they lose $1. If they land 4 hits, they earn $1. And if they land 5 hits, they earn $4. And so for part B, we actually need to determine whether this game, and this is a huge, huge buzzword, we need to determine if the game is fair. Now, what do you think makes a game fair? A game is fair if your earnings equal your losses. For example, in a casino, contrary to what some millennial memes talk about, you always lose when you gamble, okay? I mean, in theory at least, you always lose when you gamble because the casino has a little bit of an edge, okay? The casino usually wins at least by a little bit, okay? But if the casino were made in a way that all its earnings, in probability at least, equal its losses, it would have to be fair. So how can I calculate the earnings and losses and all that stuff? Well, here, the idea we need to talk about now is an expected value. That's the main thing you should maybe be Googling or thinking about right now. The expected value of something, which is in your formula booklet, by the way, all right? Your expected value has to do with, if you run the numbers, what should come out, see? So think about it this way. The probability of landing 0, right? And really focus on this part. This is the biggest part, right? The probability of landing 0 is 15%. And if you land 0, which has a 15% chance, you have to pay $4. So you can also think about it this way. The probability that you pay $4 is 15%. The probability that you pay $3 is 20%. The probability that you earn $4 is 0.25%. I mean, it's 25%. So that is what you have to do. So for the expected value, all you really have to do is take those two tables and have them interact with each other. So as I said, the probability that you lose $4, so -4, and now it's going to be for expected value, yeah? So expected value is going to be the probability of paying $4 is 15%. Plus, the probability of paying $3 is 20%. Probability of paying $3 is 20%. Plus, the probability of paying $1, right, is k%. And k we said was 8. So the probability of paying, was it $2? Sorry, the probability of paying $1, that it? So this one right here is k%, k is 8. So -1 times 8. Plus the probability of, the probability of paying 0, so basically nothing happens, is 16%. So 0 times 16, 0.16 I mean, plus the probability of earning 1 is 2k, which is 16%. So probability of earning 1 is going to be 16%, so 0.16, plus the last parentheses, which is the probability of earning 4 is 25%. So earning 4 times 25. Got it? So if you put all of this into your calculator, you will end up with, give me a second, why is it not working? Yeah, there it is. So on the one hand we have, and just so we show you once again, ¿cierto? So paying $4, right, this -4 here, the probability of that is 0.15. Plus paying -$3, so losing 3, right, the probability of that is 0.20. Plus probability of losing $1 is k. K was 8, so 0.08. Actually 0.08, I might have written that wrong down here. This is supposed to be times 0.08. K is 8, so that's 8%, right? 8% is going to be 0.08. Small detail, I missed it down here. Anyways, coming back up there, we keep adding onto the parentheses, so now we're onto this one, right? So probability of paying nothing, so just 0, is times 0.16, plus the probability of earning $1 is 2k, which is 0.16, right? Plus the probability of earning 4, so that's this 4 here, is going to be 25%. And here's the thing. Within this chain of math that I just did, earlier I told you earnings have to equal losses. Now if earnings equal losses, that means that this that I'm putting in red, which are my losses, has to equal my earnings, which are in green. Well, technically not that one, only these two, these earnings. So if these are equal to each other, then the game is fair. But notice, the losses have negative values and the earnings have positive values. So the other way you can think about it, and it's probably more friendly, is that it's fair if the expected value equals 0. So if this cancels out with this, then the game is fair. If it doesn't, well then it's not fair, see? So let's go ahead and press enter over here, see what we get. -0.12. So what this is telling you is that the expected value that we just calculated gave me -0.12. So the other way you can think about it is that when you play this game, if you play it a bunch of times, on average, you are losing $0.12. I mean, you're losing 12 cents. The bigger point here, though, is that your expected value did not equal 0, so then it's not fair. So this down here is not fair. This up here is fair. If it equals 0, it's fair. If it does not equal 0, it's not fair. Got it? So that is a way in which you can justify your answer. It's very important. This is worth 3 points. So on the one hand, we probably had some sort of procedure method by plugging this in. And on the other hand, you have your justification or your argument, which is what I'm putting right there. If it equals 0, it's fair. If it doesn't equal 0, it's not fair. If we go ahead and check the answer key, so this is for number 12, you can see there's my value for k, right? The 8, the 0.08, right? Because within this context, yes, I left it as 8, but technically it's 8%, 0.08, ¿cierto? Or actually, correcting myself, good thing I checked. When you take this 0.24 and divide it by 3, it does give you 0.08. My bad, I was thinking 24 divided by 3. Dale? I'm going to leave it in the video because everyone makes mistakes sometimes. I still wrote 8%, so I probably would have gotten the right points or answer anyways. But small detail, I was thinking out loud as 24 divided by 3 when it's 0.24 divided by 3. All the more of an argument to always check with your calculator. See? So K is 0.08. And the procedure for the expected value is right there. So because it does not equal 0, the game is not fair. See, so that is one of your reasoning points. The other one is the answer, which is reaching the negative 0.12. And the other point is using the right method, which is the expected value method. Okay? Ladies and gentlemen, a fairly easy problem. All you really need to do is understand the big buzzword of fair. Whenever you run into fair, you need to be thinking expected value, and specifically that when it equals 0, it is fair, and when it does not equal 0, it is not fair. Okay, those are the things you need to keep in mind. All right? Acknowledge how to solve it, and also that in probability, it has to equal to 1. See? Those are the two main things. Once you establish that and see how they connect with each other, it becomes much more easy. Ladies and gentlemen, enough talking by me. I hope it helped. That is for number 12.